you guys for coming. So I've always been intrigued by why things in nature occur. So today I wanted to share with you guys the square cube law. The square cube law was discovered by Galileo, and as he wrote it in his book Two New Sciences, the ratio of two volumes is greater than the ratio of their surfaces. So a good way to visualize this is by looking at a cube. So in a cube, the volume is equal to the length times width times height, but since they're all the same, it's just the length cubed. The area is equal to the length squared. So you notice that when you double the length, the volume is cubed, but the area has only squared. And if you split it into 4 parts, you can notice that the two squares, this one now has 2 cubes above it, as opposed to the first one that only had 1 cube above it. And this matters for a variety of reasons. So for example, in a building, as you scale a building up, the weight at the bottom increases. So this explains why you can make a paper model of a building and it'll be structurally sound. But if you were to scale it up to a full-size building and made it out of paper, it would collapse on itself. So since when you scale it up and double the height, there's double the weight on the bottom, one way around it is to use a material twice as strong. So in this example, if you were to scale it up 1,500 times, you'd need a material 1,500 times as strong, which is why we make buildings out of steel and not out of paper. But this also puts a limit, since if we wanted to scale that building up 10 times, we would need a material 10 times stronger than steel. And we don't have that, so this puts a limit on how big we can make our buildings. And I wanted to show you guys a fictional city. This comes from the movie Mortal Engines. And in this fictional world, they build their cities vertically so they can keep them compact and put them on wheels and drive them around. I wanted to show you guys this because it would be impossible to make this. The weight on the bottom would be too much to support its weight and it would collapse. Now this property also applies to animals. So if you look at an ant, it's very small and its legs are very small compared to its body, yet it can hold 20 times its body weight. An elephant, on the other hand, is very large and has thick legs, yet it can only hold a fraction of its weight. And the same property applies. So if you were to scale an ant up 1,000 times, then for it to be able to be just as strong proportionally, it would need bones 1,000 times as strong. But the bones in an elephant and the ant are the same, which is why the elephant seems weaker. And if you were to put a human in there, which falls in between the two in size, the average human can only carry about their same body weight. And you can see how this affects humans directly. Some people grow abnormally tall, and even though they have the same proportions, their bones aren't any stronger, which is why very tall people have problems with their legs. Their legs aren't able to support their weight, and they have to use canes or crutches to get around. And I wanted to show you another example of Hollywood ignoring this. So you have King Kong, who appears to have the same proportions as a gorilla, but is much larger. This would be impossible. So according to calculations by Sci-Fi Wire, if you were to scale a gorilla up to be over 23 feet tall, its bones would collapse because it would be too much weight for it to support. And you can see this in winged animals too. So in this case, the surface area, instead of the bones, it would be their wings because that's what holds them in the air. So if you look at a small bird like a hummingbird, its wingspan is about equal to its body length. But if you were to look at a larger bird like the eagle, its wingspan is about 4 times its body length. We can again look at the fictional dragon. Now just for reference, the one on the left there is a kind of pterosaur. According to NCBI, it had a 40-foot wingspan. It's one of the largest birds to ever exist. Now if you look, its body is very thin and it has a very long wingspan compared to it. If you look at the fictional dragon, which is many times the size, it has a very short wingspan, kind of like the hummingbird. So there's no way that it would actually be able to fly. And this applies to human flight as well. So if you look at a helicopter, the one on the left is a toy helicopter. It only has 2 blades, and they don't go very far past the cockpit, and yet it's still able to fly. But a full-sized one, if you look at this one here, it has 4 blades, and they extend far past the body of the helicopter. And this also puts limits on human flight, because if you wanted to make one much larger, the blades would eventually get so big it wouldn't be practical to use. And in this, you can see another work of fiction. This is from Marvel's Avengers. So this one, it's a flying aircraft carrier, probably 1,000 times the size of a helicopter, yet it's only being supported by 4 propellers, which would be impossible. One way around this, though, would be to use something that isn't affected by surface area, kind of like a Zeppelin with helium in it, which floats because of its volume. And here's my works cited page for my research. Hopefully you guys learned something new about nature today. Thank you for listening.
Thank you.
No one laughed.